We will calculate percent composition and identify empirical and molecular formulas. Silly mole joke of the day. Which one of Avogadro's teeth did the dentist pull? The answer, a molar. Percent composition by definition is the percent by mass of each element in a compound. So when you want to calculate the percent composition by mass of a compound, you take the total mass of that element in the compound divided by the total mass of the whole compound multiplied times 100. For example, if I wanted to know the percentage of oxygen in sodium carbonate, then I would take the total number of oxygens, which is 3, and I would take the mass of oxygen times 3 divided by the mass of the whole compound sodium carbonate. So here it would be oxygen 15.999 times 3, and then divided by the total mass of the compound times 100, and we get that there's 28.91% oxygen in this compound. Another example, if I wanted to know the percentage of carbon in iron 3 carbonate, then I would add up the total number of carbons. In this case, notice the 3 distributes into the parentheses, so we have 3 carbons, divided by the mass of the whole compound times 100. So it would be 12.011 times 3 divided by the mass of the whole compound times 100, and we get 12.35% carbon in iron 3 carbonate. So now let's do a few examples in your note packet. Calculate the percentage of each element in C3H8. So we'll start with the percent of carbon is equal to, and we want to do, there are 3 carbons, so it's going to be carbon times 3 over the molar mass of the entire compound. And to find the percentage of hydrogen, because there are 8 hydrogens, it's going to be hydrogen times 8 over the molar mass of the entire compound. So the mass of carbon is 12.011 times 3 divided by, and then we have 12.011 times 3 plus 1.008 times 8 equals, down here we're going to have 1.008 times 8 of them divided by, and then this same mass of the whole compound that we found up here equals. Now let's type it into our calculator. We get 12.011 times 3, and then I'm going to divide it by 12.011 times 3 plus 1.008 times 8. And then we're going to multiply everything times 100 to make it a percentage, times 100 times 100. So this has 81.71% carbon. And then this one down here is 18.29% hydrogen. And the percentages in the entire compound should add up to equal 100. So 81.71 plus 18.29 does indeed equal 100%. What is the percent of hydrogen in acetone? So to get the percentage of hydrogen, I want to know how many total hydrogens are there. And you'll notice hydrogen has a subscript of 6. And so I'm going to take the mass of hydrogen times 6 divided by the mass of the entire compound. And so that's going to equal 1.008 times 6 over 12.011 times 3 plus 1.008 times 6 plus 15.999. And these are the masses of carbon, hydrogen, and oxygen from the periodic table. When we do this calculation, we get 10.41% hydrogen in the compound. Our last example, what is the percent composition of oxygen in, and this should say calcium hydroxide. Notice we have parentheses in this one. So if I want to know the percentage of oxygen in calcium hydroxide, I'm going to count up how many oxygens there are, and the 2 that is outside of the parentheses distributes into each element inside of the parentheses. So we have oxygen times 2. And then I'm going to divide by the mass of calcium plus oxygen times 2 plus hydrogen times 2. So when we set this up with our numbers from the periodic table, we get 15.999 times 2, and then this is going to be divided by 40.078 plus 15.999 times 2 plus 1.008 times 2 equals, and we get 43.19% oxygen when we do our math in the calculator. We'll talk about empirical formulas, which are the lowest whole number ratio of elements in a compound. A molecular formula is the actual number of atoms of each element in a molecule, so it's known as the true formula. For example, if I had CO, carbon monoxide, as the empirical formula, that's 1 carbon, 1 oxygen, then a molecular formula could be double each of these atoms, C2O2, or quadruple each atom, C4O4, but you could not bump it up to CO2. In other words, the molecular formula should be able to be simplified down to the empirical formula. So the empirical formula may or may not be the same as the molecular formula. For example, H2O2, if that's the molecular formula, then I can reduce the 2 and 2 down to 1 and 1, and I'll have the empirical formula. Carbon dioxide, CO2, you cannot reduce 1 and 2, and therefore this is also the empirical formula. So let's practice a few. If I have C6H12O6, then the empirical formula would be, I want to reduce my subscripts to the lowest possible amount to get the empirical formula. So 6, 12, and 6 could be reduced to 1, 2, and 1. So it would be C1H2O1, or just CH2O. In 2O4, I can reduce 2 and 4 to 1 and 2. So this would be NO2. 6, 8, 6. Well, these are all divisible by 2, so I could reduce this to 3, 4, 3. So C3H4O3. C2H6, these are divisible by 2, so I could have 1 and 3. So that would be CH3. CH4, I cannot reduce 1 and 4. That's as low as it'll go, so CH4 is the empirical formula. And then C7H14, they are both 1 and 2. C7H14 is the same as 1 versus 2 ratio, so this would be CH2. You may be asked the reverse: if CH2 is the empirical formula, then which of the following could be the molecular formula? So notice that if I multiply both of these subscripts by 7, I get the molecular formula. If I don't change anything here, these are the same. If I multiply these subscripts by 2, I get the molecular formula. If I multiply these by 2, I get the molecular formula. If I multiply these by 2, I get the molecular formula. And if I multiply these by 6 each, I get the molecular formula. So understand how to divide it down, but then also how to multiply up. Now let's do some practice on Canvas.